going over using method of Lagrange multipliers. It says each of these extreme value problems has a solution with both a maximum and a minimum value. Use Lagrange multipliers to find the extreme values of the function subject to the given constraint. How nice, they told us we have a max and a min. So f of xy equals xy, and here's the constraint, 4x squared plus y squared equals 8. This one, Terme? Oh, Lucas needed this one. Okay, my bad, sorry. Okay, so then start off, this is our g of xy, right? So gradient of f equals lambda gradient of g. So gradient, what did you get?
I got yx equals lambda ax 2y.
Beautiful. Okay, so equation 1 is going to be y equals 8 lambda x. Equation 2, x equals 2 lambda y. And then what's the third equation?
4x squared plus y squared equals 8.
Good. 4x squared plus y squared equals 8. Okay, so there's no like context here, right? We're not making a box or something like that, so no dividing by variables on both sides. You'd lose a solution. So if we're going to do anything, we're going to have to set it to 0. I think the easiest thing to do is why don't we get lambda by itself, yeah, in the first two. So here we have lambda equals y over 8x. And then I can do the same thing over here. Lambda equals... Good. So then those must be equal to each other, right? Y over 8x is going to equal x over 2y. Cross multiply, what do we get?
2y squared equals 8x squared.
Good. So then y squared is...
4x squared.
Good. And then put it back into 3. So then 4x squared plus 4x squared is 8. And then you would have 8x squared is 8, x squared is plus or minus, oh, x squared is 1. I got too excited. And then x is plus or minus 1. And then if x is plus or minus 1, y would be 2. So how many points do we have here? 4, because plus or minus 1, each of those x values goes with plus or minus 2 for y. So we're going to have to evaluate all of them. And then I know you're going to be mad because I did divide by 8x and 2y, but I know they can't be 0. Why? Because the constraint equation would not be satisfied, right? Only if they're both 0, we'd have a problem. Okay, so we're fine. So then let's check all of the function values. So f of 1, 2, I got 2. F of 1, negative 2 is negative 2. F of negative 1, 2 is negative 2. And f of negative 1, negative 2 is 2. Good? So where's our absolute max?
1, 2, negative 1, negative 2.
Good. Let's just say these are absolute max here. And then the other two are the absolute min. So if they say, what's the absolute max value? You give the z value. You would say 2. Or the absolute min value, negative 2. Then if they say, where does it occur? What would you say? Yeah, you would give the coordinates at 1, 2, at negative 1, 2. Yeah, Roy.
So x and y can't be 0
Because then the constraint equation wouldn't be satisfied. 0 plus 0 doesn't equal 8.
right, but what if only x is 0 or only y is 0? Is it possible to know? Or?
No, because, okay, if only y was 0 from this equation, x would have to be 0 as well for it to be satisfied. Right? So then you run into issues there. And a lot of these, you don't have to be so paranoid. So if you just want to mentally check, can they be 0? And then just say, okay, I'm okay to move on. You don't have to write it out for me every time you do one of these. Just check in your head. Yeah, Lucas.
So my difficulty on this one is I didn't catch the x equals 0 at first, and then I totally solved it up, and I was like, oh wait, that doesn't work.
What do you mean x equals 0?
Oh, I did. I set it up so x equals something and then y equals something.
Okay.
And then
X equals y over 8 lambda.
no, so I did. I solved for y in terms of x. Oh wait. No. Anyways, no, that's not it. The question I just want to know is, to find your contradiction, if you can't mentally check, is it fine to just take whatever point you have and check with each condition and make sure it doesn't give you?
Yeah, that's fine.
That's all you
Probably
do.
not as efficient. Yeah, but if you're having a hard time kind of,
Mentally doing it.
yeah, and getting comfortable with these, that's fine. That'll work. Okay. Good? All right, 9. Who needed 9? Oliver, yes? Okay. Did you set it up okay?
I think so.
Let's see. So f of x, y, z. Was this section easier than last night's? Or 2 nights ago? For sure. Thank you to Lagrange. I don't know anything interesting about Lagrange. I should read up on it. Sorry. Okay, so gradient of f equals lambda gradient of g. So you should have 2, 2, 1 equals lambda times? Beautiful. Okay, so we have 4 unknowns. We better have 4 equations. 2 equals 2 lambda x. 2 equals 2 lambda y. 1 equals 2 lambda z. And then 4th equation. Good, our constraint equation. Okay, yes, Kimberly.
Isn't it wrong if we put the lambda in front of the 2?
No, but it's usually we put the constant in the front.
Yeah.
Yeah, but we're going to be rearranging anyways in a moment. You know what I mean? So why don't we go through? I'm noticing I have each of the variables here. Only one of them is involved at a time, and then there's a lambda. That means I can get x in terms of lambda, y in terms of lambda, z in terms of lambda, and then I can put everything in the constraint equation and have only lambdas. Does that make sense? What's your question, Sebastian?
Why is there an extra equation again?
Because how many unknowns do we have? We have,
3.
no, x, y, z, lambda's the 4th one. So however many unknowns, you have to have that many equations. The extra is always the constraint.
Okay.
Always the constraint. Okay, so on that note, I'm going to say x equals 2 over 2 lambda, which is 1 over lambda. Y would be same. And then z would be 1 over 2 lambda, right? Or 1/2 1 over lambda. Let's just leave it like that. Okay, so all of these into equation 4, and we should be good to go, right? So 1 over lambda squared plus 1 over lambda squared plus 1 over 2 lambda squared is 9. And then this is going to be 1 over lambda squared plus 1 over lambda squared plus 1 over 4 lambda squared is 9. What would you do to solve next? Or just clear out the denominator. When you have an equation, you can just multiply through by the LCM, the common denominator, and be fraction free. We don't need to keep it with us. Let's be done with them. So what's the common denominator? 4 lambda squared. So multiply everybody by that, and then you won't have any fractions left. So then the equation's going to be 4 plus is, yeah, beautiful, right? Okay, then that's going to give me 9 equals 36 lambda squared. 1/4 is lambda squared, which means lambda is plus or minus 1/2. Okay, so if lambda is positive 1/2, let's see, x is going to be 1 over 1/2, which is 2. Y would be the same, and z would be 1. And then if lambda is negative 1/2, x would be good. Y would be, and z, good. So these are the only 2 points where I have to evaluate the function. And then f is 2x plus 2y plus z. So you're going to get 9 for the first one, negative 9 for the second. So what's the first order triple? Give us absolute max. And this one is our absolute min. Yay, good. Yeah, Kyle.
Do you want us to write something that states that we know that lambda can't equal 0 because it wouldn't satisfy the...
It would contradict all of them.
Yeah.
No, you don't have to. Like, as long as you know not to explore that option and list out like faulty points, yeah, that's fine.
Okay.
Yeah, Roy.
I thought we're not supposed to reduce variables with each other.
You're not supposed to what?
Right, if you have x squared over x, you can't just do.
Where did I do that?
With the lambda squared over lambda.
Oh, when you multiply through and you clear out fractions from an equation, you are allowed to do that because we know lambda can't be 0. Yeah, when you solve rational equations back in, I used to teach it when we taught intermediate algebra. So you would have like, say you had an equation 1 over x plus 1 over x squared plus 1 over x times x plus 2 equals 7. And the approach is always when you start, you multiply by the LCM. So you would multiply by x squared, x plus 2, or whatever. You know what I mean? That's always like the first step. But you do have to assume, I would remind them, always write out your domain restriction. So always write out x can't be 0 or negative 2. You like kind of write that in the beginning of the problem, and then later when you solve, you just make sure that doesn't pop up as one of the solutions in the end. So we know lambda can't be 0. That would make contradictions, right, for the first 3 equations. So then we're fine, and I didn't even get that that was the solution anyways, right? So I guess that's the only place where it would be problematic, Kyle, if you forgot to think about it, and then you ended up getting that value. Right. Yeah, Kimberly.
Just checking, if we did a different strategy, we've got the exact same points. That's
You're fine. There's more than one way to go about these because they're not linear systems of equations, especially. So totally more than one way to get there.
Okay.
Whatever works for your brain, as so long as you don't miss any points, that's the thing. But yeah, more than one way to slice and dice it. Okay, that one was 9. 33. Who? Oh yes, my dear.
So there's no way to solve this without using every equation you write.
Yeah, because 3 equations only involves 3 of the variables. And if you have 4 unknowns, you have to have 4 equations.
Yeah.
Yep. Okay, 33. Which one is 33? Huh. Who asked for that one? Lucas? Okay. Let me just do it on a fresh sheet so it doesn't look a mess. Find the extreme value subject to both constraints. Okay. So we're going to have this time a lambda and a mu. What is that in physics? Coefficient of friction?
Yeah.
Yeah. I haven't done it in so long, but
Lambda in chemistry is wavelength.
wavelength. Okay.
It's also wavelength in physics too.
Okay. So they agree with each other. They use the same stuff.
It is.
That's good. That would be upsetting if they switched it up. Where do I have 33 done? Give me a moment. Oh, there it is. Oh, this one's moderately spicy. Okay, here we go. So gradient of f equals lambda gradient of g plus mu times gradient of h. I just called this one g and this one h. Is that good?
Is it fine if we do that too? If you want the g equals blah minus?
No, because it's just a constant, right? So if you moved over the 1
It's still gonna end up
and you find the gradient, it's not going to make a difference. Yeah, just if there's a variable, you have to move it over. Yes, we can be relaxed about it. Okay, gradient of f, I have y, x plus z, y. Do you agree?
Yes.
Oh, good. Okay, equals lambda times,
y x 0.
or y x 0. Yeah, what was I doing? Okay, y x 0 plus mu times,
0 to y to z.
beautiful. Okay. All right, first equation. Okay, Sebastian, how many equations will I need here?
4.
X, y,
X, Y,
z.
lambda, mu. I didn't see mu.
I know. Okay, so 5. There we go. So y equals y times lambda, or lambda y, plus 0 times mu. So I'm not even writing it. 2. X plus z equals lambda x plus 2 mu y. 3. Y equals, yeah, 2 mu z. 4 is, good. Or no, the order doesn't matter. Okay, and then just as long as you have both of them on there. Okay, perfect. Vincent, I was worried where you were.
Oh yeah, it's just had to finish some stuff up for some family. That's all.
Okay, it's all good. I'm glad you're here. Okay. Today you don't get yelled at for coming in late.
You didn't
'Cause
say attendance.
It was optional. It's optional. Okay. So I started with equation 1. You can kind of start wherever you want to go. So I said, all right, from equation 1, let me set it to 0. Y minus y times lambda is 0. That means y times 1 minus lambda is 0. So either y is 0 or
Lambda is 1.
lambda is 1. Okay, if y is 0, already we have a contradiction. You can use this symbol to show contradiction. Can't happen, because if you look in equation 4, we have x times y has to equal 1. Well, if y is 0, that won't work. So then I know this is garbaggio. Don't explore that case. So lambda has to be 1.
And you could also say that is in equation 3, though, it means z is equal to 0, and that contradicts 5. 0 plus 0 is 1. Right?
If y is 0,
Then mu and z have to be 0 and 3, and that means that 5.
you have a problem as well. Yeah. So however you get there, y can't be 0. Y can't be 0. So now let's explore if lambda is 1. What's the next equation to put that into? What happened? Yeah. Like why you knew to throw it away. So Lucas was saying, oh, I also can spot it from a different equation. That's fine. Just tell me why you know it's not going to work out. Yeah, Oliver.
You can divide by y, and y over y is 1. Goes lambda. Instead of setting it to 0,
As long as you know y can't be 0.
you would have to write this case y equals 0 and maybe figure it out.
Yeah. Or if you can show, we don't have to worry. We know it's impossible for y to be 0 because otherwise equation 4 wouldn't be satisfied. So if you say that, then you could divide by y on both sides. But sometimes it could be, so just don't forget to check.
Check the case.
Check the case. Now, if they were saying if this was like a real world application where y was some dimension, then don't worry about it being 0, right? Because you know it's going to have to be, yeah. Okay. So we're going to equation 2. Are we ready?
Yes.
Yes? Okay, good. So into equation 2, we've got lambda equals 1. So x plus z equals, x plus 2 mu y. What can we do?
We can cross out x on both sides because x can't be 0.
Oh, or just even if it was 0, it would still cancel out. I'm not dividing. I'm just like subtracting x from both sides. So yeah, but I love the constant paranoia. Perfect. So z equals 2 mu y. I also know y is not 0, so let me just say mu is z over 2y. Why did I do that? Yes, because I know over here y equals 2 mu times z. So let's take this into 3. So y equals 2 times mu is z over 2y times z. Yes? Ooh. Okay. So then I have, let me multiply the y over because there's a y in the bottom. Then I have y squared equals z squared.
And we can multiply over because we know y cannot equal 0.
Right. And you can just multiply through by the denominator always. And then we're going to have y is plus or minus z. Or you could say z is plus or minus y. From here, you should be home free. Where do you go? Run. 5. Run straight to 5. Into 5. Whether y is plus or minus z, when I square it, I'm going to get the same thing, right? So you have 2z squared is 1. So z squared is a half. So z is plus or minus 1 over root 2. You get both those z values for each of the y values. For each of the y values. Oh, is it too low? Sorry. Okay. Who's missing? X. Where should we go get x from? Where? 4. Oh, yeah. X times y equals 1. Okay, perfect. So x times y equals 1. Y is... Well, here's the thing. Y is plus or minus z. So if z is 1 over rad 2, y could be positive or negative. But x and y have to have the same sign because they have to multiply to a positive 1. So x and y have the same sign. So x is going to be 1 over y. So 1 over plus or minus 1 over rad 2. So plus or minus rad 2. Just remember that x will match the same sign as y because their product is going to be positive. So then when you write the points out, you can do that little plus minus or minus plus thing. So let me show you. So x and y have to always have the same sign. So if x is plus or minus rad 2, y will be plus or minus 1 over rad 2, right? Now, does z have to have the same sign as those two? No. So we'll have one case where z is minus plus 1 over rad 2, and then the other case is they're all the same. Does that make sense? So what this says is x and y can be positive. So like if x and y are positive, the z could be negative. Or x and y could be negative and z is positive. Or x and y are positive, z is positive. Or x and y are negative, z is negative. So the sign on x and y has to be the same. They both have to be positive or they both have to be negative. But z can have a different sign or the same sign.
And that gives us
4 total, yeah. And then you're plugging it back into yz times xy. So these come out the same, actually. So this will come out to 3/2, and this comes out to 1/2.
And if you want to test that, like, your points are correct, you can take those 3 points and plug them into, like, I don't know, equation 2 to make sure it works out. So you didn't mess up.
Oh, if you're nervous that they all, yeah, you could. Yeah, they should satisfy any of the 5 equations. Yeah. Good? If you want to actually list out 1, 2, there's 4 points technically total, right? You could list them all out separately if you don't like the minus, plus, plus, minus notation. I'm just trying to save you guys writing. I don't like writing a lot, so you don't either, Justin, right? You're like, we don't have time. That one's hard. That one was a hard one, I think, to solve. No?
Yeah, that's a little bit.
No one's fazed by it? I should have put it on the test. I don't know. Or maybe I did. I don't know. Hee hee. Okay, 43. Where's 43? 43 says, use Lagrange multipliers to give an alternate solution to 45 from 14.7. And are the same 3 here that you guys needed. Perfect. That worked out beautifully.
But multipliers Lagrange, Lagrange.
Yeah. So 45. Find the points on the cone that are closest to the point 420. Let me find when I did it. Did I ever do it? Oh, here. Okay. So I'll call this 43, but this is 45 from 14.7. Okay, find the points on z squared equals x squared plus y squared that are closest to 420. So what quantity are we optimizing? What's my function? Distance, very good. However, I don't actually want to work with the distance formula. It's nicer to work with distance squared, which we talked about yesterday. So I'll call my function of xyz distance squared. And it's the distance from some arbitrary ordered triple that satisfies the cone's equation. The cone's equation is actually our constraint equation. We're finding distance from some arbitrary xyz to 420. Does that make sense? So this cone, this is our constraint. If you want to minimize the distance from any ordered triple to 420, subject to, right, you're used to hearing subject to, the constraint that that ordered triple has to be on the cone. So that's what you're going to put lambda on, okay? So distance is going to be just distance formula here between arbitrary xyz and 420. So it would be x minus 4 squared plus y minus 2 squared plus z squared. Good? Subject to, that xyz has to be on the cone, so I'll just say g of xyz is x squared plus y squared. Now this time it matters that we move the z squared over because it's not just a constant, okay? All right, are we good with the setup so far if we're going to do Lagrange multiplier method? Yes, Terme.
Do you notice
No, but I just think it's easier that way. You know which one your constraint equation is, right? Because maybe when you first read it, you thought the cone equation had to be f or something. I don't know.
Yes.
You thought that, right? Yeah. So always look at when they say minimize, closest, biggest. That's what f should be. That's what the function should be, whatever you're trying to optimize. Okay, so gradient of f equals lambda gradient of g. So gradient of f is going to be, okay, hold on, let me think. I didn't multiply it out, and I'm happy I didn't.
2 times x.
It's not horrible that you did. You're just going to have to divide more later. Okay, 2 times y minus 2, 2z equals lambda times,
2x, 2z, negative 2z. Or 2y, negative 2z.
okay, perfect. So equation 1, I already went through, I aggressively started dividing by 2. Look at that. I was like, let's get this show on the road. Y minus 2 is lambda y. Z is, ooh, negative lambda z. That's peculiar. Okay, and then 4 x squared plus y squared or equals z squared. It doesn't matter, whatever. Yeah, just put that one on there. Same thing. Okay. So let's see. From here, what did I do? Oh, I got the x's on one side and I solved for x. I did the same thing with equation 2 and 3. What did I do? Hold on, let me see what the heck was going on over here. Yeah, then okay. So hang tight. So from here, if I set all the x's on the same side, I'm going to have x minus lambda x is 4. I can factor out an x. X times 1 minus lambda is 4. And then are we worried if lambda is 1? So if lambda is 1, let's see. Then z would have to be 0 if lambda is 1. But then it wouldn't be on the cone, right? Unless we're at 0, 0, 0. So I don't think we have to worry about that. X can't be 0 because the first equation. You're right. Okay. So if, let's just, there was a lot of thinking going on. Let's write that out. Okay. I'm going to divide right now, though, by 1 minus lambda. So x equals 4 over 1 minus lambda. What if lambda is 1? Okay. So then from equation 3, z would have to be 0, right? And then from equation constraint number 4, that means x and y would have to be 0. But they can't be 0 because you'd have a contradiction in 1 and in 2. Does that make sense? Okay. So then we're good to divide by 1 minus lambda. Moral of the story. No need for panic. This is allowed. Okay. Yeah.
So then, say, because what I did was I just used equation 3
Okay.
in my cases.
Okay. Yeah, you can totally take a different path.
But that means that I don't have to show an equation 1 that lambda cannot equal.
Right. Yeah. If you somehow got there straight from 3, you're good.
Okay.
Yeah. What's up, Vincent?
I used the z's, equation number 3.
Okay, we can do that instead. Everyone hates my method. Let's do it. Your way is terrible.
I didn't even know please use your method.
Let's just try. Let's see what happens. What did you do next?
Then you factor out the z's, so you
Okay.
just do 1 plus lambda. And then
But then you have to worry about lambda being -1.
So then you test that case.
Yeah.
Oh, well, then it's equivalent to what I did. You're just testing a different scenario that won't happen. Okay. Blah, blah, blah. Same thing.
But you don't have to show all scenarios.
No. You just, the one you take. Yeah. Okay. So we're fine. We're doing the same thing, just a different way. Good? Okay. Now, where was I going with this? Oh, I'm going to do the same thing with the second one. Good? So then we have y minus lambda y equals 2. So then I have y times 1 minus lambda is 2. I already showed lambda won't be 1.
Now you just show y can't be 0.
No, I'm not going to divide by it. I'm just going to divide by 1 minus lambda. So y equals 2 over 1 minus lambda. So that's enough. I'm only worried about lambda being 1 because I'm dividing by 1 minus lambda, right? Okay, so y is fine. And then lastly, same thing here. I did the same with z. So then we have z plus lambda z is 0. Oh, then I got what you got. I did the same thing. So then z times 1 plus lambda is 0. So either z is 0 or lambda is negative 1, which you said is a contradiction, right?
Lambda's negative 1 works. Z is 0 is a contradiction. That's what I thought.
Yeah.
Because if Z
Oh, okay, you're right. So if z is 0, then x and y would have to be 0, right? But, yeah. No, that's a contradiction. You're right. Okay, so this one goes bye-bye. Z can't be 0. That means lambda has to be negative 1. Okay, so then we're done. Then I can find x and y and z because I know lambda is negative 1. Yes, Roy?
Back to the, where you said the lambda can't be, what if lambda is equal to what? You said for equation 3, z would equal 0?
Yeah, because if lambda was 1, you'd have z equals negative z. That's only true if,
Okay.
right?
Yes, right.
Okay, so then from here, can we get the rest? Yeah, because I know lambda is negative 1. So x is going to be, give me 1 second, Sebastian, 4 over 1 minus negative 1. So that's 2. Y would be 1. And then z,
plus or minus if you plug into
yeah, because z squared is x squared plus y squared, which is 5. So z could be plus or minus rad 5. 2 points. 2, 1, plus or minus rad 5. And would the distance be the same from both of them? Yeah. And it makes sense because of the symmetry of the cone, that you're going to have 2 solutions based on how it was. Sebastian has his hand up first, and then I'll get to you, Griffin. 1 moment, please.
Why is that a contradiction again?
Which
Where you
one?
crossed out with the x.
Oh, because look at these equations here. If x was 0, then you're saying 0 minus 4 equals 0. Does negative 4 equal 0? No. So these are contradictions from 1 and 2. Griffin, what's your question?
And just to be absolutely clear, there are multiple ways to go about this.
Yes.
I keep on getting the same answers as you, but
Oh,
going about it.
I love it. No, I love that even more. Yeah. So long as you're not missing any of the points in the end,
Okay.
then you're good.
All right, perfect.
Yes.
Bless you.
Okay. Are we all right? Oh, yeah, Oliver.
Using case 3, when you divide by z,
Yeah.
you have to check for z equals 0, right?
Right. But z equals 0 implies x and y has to be 0 from equation 4, which contradicts equations 1 and 2. I feel like we all should have taken a logic class before this, huh? Wouldn't that have been good? Yeah. Did you do a lot in discrete with logic? Did it help, you think, reason through these?
Yeah, well, I mean, I don't know, I didn't have so much
Yeah.
yeah.
Okay.
I did take a logic class. That was a year ago, so
But have you been thinking more logically since?
yeah.
Okay, good. Do we want to do the same problem the other method?
Yes.
Okay. So let me just do it while we're here. Yeah, while we're here. So using the method of 14.7,
Do we not call that method in English? 14.7.
yeah, I called it 14.7 on the test, just so there's no confusion. Yeah.
Professor, so is it okay if we use Lagrange multipliers like 4 questions like 14.7?
So I'm picky on the test I put, use Lagrange here. On the other one I said use the method of 14.7.
Oh,
And then there's one question where I said do whatever you want.
okay.
Okay? Yeah, you can check it with Lagrange, of course. Yeah. Was that your question, Roy? Yes. Do whatever you need to do to check.
No, you never know.
And it's not cheating.
It is not cheating.
Showing my knowledge.
Okay, so here's what we're trying to optimize, right? I'm going to still call this kind of my F, right? But you guys, the methods that we learn for optimization are for functions of how many variables? When we learn the d-test and everything?
This function of 2.
Just functions of 2. Because you take partial with respect to x, partial with respect to y. Lagrange is special because you could do 2, 3, 4, whatever. We're not restricted. So here we're restricted. I have to reduce the number of unknowns, and you reduce the number of unknowns with your constraint equation. So what was the constraint equation when we did it with Lagrange multipliers? Yes, that the point had to be on the cone. It had to satisfy the cone's equation. So it seems like the most natural way to reduce a variable is replace z squared with x squared and y squared. So then now I can say, oh, I finally have f of xy, that's what I'm trying to optimize, which is x minus 4 squared plus y minus 2 squared plus x squared plus y squared. So this step we don't need to do when we solve with Lagrange multipliers. You can have as many variables as the problem has naturally. Okay, so now we're going to get our critical values. Same way as before. Take your partial with respect to x, partial with respect to y, and we need them both to be 0 simultaneously. So partial with respect to x is going to be?
2 times x minus 4 plus 2x.
Good. And then let's just clean that up. That's going to be 4x minus 8, right? If I set it equal to 0, I get, and then partial with respect to y?
2y minus 2 plus 2y.
Which is 4y minus 4. Set it to 0. Oh. So x is 2. Y is 1. How do I get z? Just plug it in. So z squared is 5. So z is plus or minus. Yeah? Did it ask for the distance or just the point? Okay. So then that's it. So the points are 2, 1, plus or minus around 5. Oh no. I dare say this was faster. For this one it was, huh? Yes,
This
Kimberly.
is solving for like absolute minimum, right?
So these are the only critical points.
Yeah.
It wanted the min distance.
Yeah.
I would just plug them in to make sure they both give you the same one, but hopefully you can just tell by looking, right? It's not gonna, I mean, the distance squared isn't even dependent on z.
I guess I'm wondering why you wouldn't do corners or boundaries in this equation.
Subject to the cone's equation?
Because I thought 14.7 was we have our d-test and then we have interior.
The absolute extrema? Yeah. So we're on the cone. Hold on, let me think.
Because like this looks like.
It's a 3-space. I know, it's a mix. It's like a hybrid. It is.
I'm not sure which 14.7.
Like, what would D be?
Yeah.
No, we can't graph D because x squared plus y squared is not constricted by a constant,
'Cause
right?
We didn't have to do the d-test either to show is it a relative min-max or whatever.
Right,
It's,
because we just had it gave you the same thing, yeah. And if you look at the function, look at the function we're optimizing. It's not going to have a max. It goes up forever. You can make that as big as you want.
So 14.7 is really just partially derived and find the critical points?
Yeah,
Oh,
It's like
so
doing
we
only
don't
part
do
one of that.
yeah,
Yeah.
it is.
Which,
And this is funky. It doesn't fit the format really of the others. Yeah, I know. In your brain, you want it. There's only 2 kinds of problems, and this kind I could do 14.7 or Lagrange, and then here's this weird one in the middle. I'm sorry.
these local then?
No, these are absolute.
They're absolute.
They're absolute mins.
Okay.
We were wondering where you were.
No,
We said obviously you don't take the class seriously.
no, I have to be.
She was gonna snitch on you to
Yeah.
That's okay.
I was for part of your progress report. I was gonna be like, oh, he missed review day. It's okay. I'll give you a glowing referral.
Okay, so Professor,
Yeah.
this is just the interior part of our absolute extrema.
Yeah. This one's not really bounded. I mean, bounded by the cone, but like it's not a region you could graph in 2 space. Edward, what do you think? Does it feel like it feels like its own kind of setup, huh?
Yeah.
Yeah. Let me think about it.
It's not
Let me think if I can. I'll call Gupta on the way home.
on the test, there'll be like a full 14.7 method, I guess. Or like, would it be a
Oh, I would let you pick what you wanted for something like this. Yeah. Like for these ones, I don't really care. Okay. Just 2 more, right? So the next one I need to do is
Find the 3 positive numbers, their sum is 100.
Yes. Okay. So find 3 positive numbers whose sum is 100 and whose product is a maximum. Okay, which way do you want to do it first? Lagrange? Okay. Let me find it. Everything's all twisted about. Oh, here. Okay. So what's the function that we're trying to optimize? Good. So we'll call f of xyz, xyz. Such that, what's my constraint?
X plus y plus z equals 100.
Good. The sum has to be 100. Perfect. Perfect, perfect. Okay. Also, here's something. We can be kind of sloppy. Divide by x, y, and z through on the equation, because I know none of them can be 0. Because if they were 0, the product would be 0.
The problem is this?
Well, depends what section you're in. So, it is 47 in 14.8. 14.7. I'm like 47 in 14.7. Okay. So, gradient of f. I mean, would it have been so hard for them to just retype it?
Numbers? Yeah, that's
Cause, and then they weren't numbered the same.
Yeah.
That, it's really actually making me mad right now.
It is, I think.
And it's like the amount of thinking I'm having to do trying to figure out which problem this is stupid.
I actually call this because you wanted 53 on my homework. I hope you forget.
You're so forgiving, Griff, because I already don't know which problem I'm doing. I mean, like,
You did 45 under 14.7.
you know what? I'm a mess.
Okay.
As long as I'm doing the problem 2 ways, we're good. Okay, guys, here we go. I mean, how much space would it have taken? These aren't even 2 lines worth of print. Right? Let's boycott.
Back to 8th edition.
Yeah, I don't think they write it in both. Okay, so you should have yz, xz, and... Oh my god, what a cute little gradient for G. 1, 1, 1. Love it. Math is easy when you get it, huh?
Yes.
And fun, I dare say, huh?
It feels good when you get it.
It feels good, and nothing feels worse than when you don't get math. Yeah.
You get stuck there like, oh my god.
Oh my god. Yeah, it'll spiral out of control. Yeah. Where your other class, like if you kind of miss a day, you're like, that's okay, I can fill in that gap later. Not this one. Okay, so look, I'm going to do something crazy. Are you ready? So we can just set 1 equal to 2, yz equals xz, and I can cancel the z out because I know z can't be 0, so I can just say, okay, x equals y, woohoo, and then let me do the same thing with 2 and 3, so I can say xz equals xy, so that means z equals y. Now where should I go?
Which is equals to x.
Yeah. So then I can say x, which is y, plus z, which is y, is 100. So y is 100 over 3.
And that's what x and z are.
Right.
Oh.
What's up, Roy?
You said that z can't be equal 0?
Right.
You said that x can't equal y, can't equal x, which can't equal 0.
No, I wrote this. None of them can be 0.
Why can none of them
Because what are we trying to optimize?
be maximum? Okay.
Maximum what?
Right.
Yes. So if one of them is 0,
Well, it's 0.
all, and the product would not be a max. Okay, good? Other way? Other way. Okay, hold on. Let me check. No. Oh, yeah. Okay, so same idea. Same idea. Okay, other way. So 14.7 way. So my function is of 3 variables. It's x, y, z. Subject to x plus y plus z is 100. So last time I told you guys, when we compute our critical values, right, you only need a function, you can only have a function of how many variables? So usually let's just eliminate z. Z is 100 minus x minus y. So then I can say f of xy is xy times 100 minus x minus y I would multiply it out so we can find the partials easier. Like, who wants to do product rule if you don't have to? So 100xy minus x squared y minus xy squared is f. Good? Okay, partial with respect to x, please.
So 100y minus 2xy minus y squared.
Perfect. Partial with respect to y.
100x minus minus 2x.
Good. Both of these get set equal to 0. Okay.
You can cancel.
I'm going to first factor out a y, and then I have 100 minus 2x minus y is 0. From the second one, I can factor out, and then I have 100 minus x minus 2y is 0. And I can just divide or cancel out the x and y's because I know they won't be 0, as we discussed earlier. Are we good?
Do you want us to show that, or is it?
I would just write it. Write it and then move on. Yeah. You don't need to write me a paragraph why, just that you thought about it, okay? No one wants to read your paragraph. And then we're going to have 2x plus y is 100. X plus 2y is 100. So let me multiply this one by -2. Is that okay? Okay, so then it becomes -2x plus 2y. No. Minus 4y. What is -200? And then 2x plus y is 100. Goodbye. -3y is -100. Y is, woohoo. Then just plug it back in and you'll get the other two. Are we good? I did do the d-test to check that it yields a max. Maybe we should have done that on the last one. That it's a max. Yeah, if you want to have maybe we should go back and do it. I'll let you do. Anyways, second partial with respect to x is -2y. Second partial with respect to y is -2x. The mixed partial is 100 minus 2x minus 2y. So d of 100 over 3, 100 over 3 is -200 over 3 times -200 over 3 minus -100 over 3 squared, which is positive. And then second partial with respect to x was negative. So then, yes, it yields a max. We maybe should have done that. Then you would feel better about that last problem. You know what I mean? Yes, Kimberly?
There's only one critical value for this equation.
Yeah. I just
So
was
we
like,
gotta be yeah, it has to be.
it has to be, but I don't know, just so that we're less nervous about it. Yeah, because we did always finish them with the d-test, so maybe, yeah.
Why the greater than 0?
Oh, because remember when d is positive, you have to look back at the sign on the second partial with respect to x. If it's greater than 0, then it's a min. If it's less than 0, it's a max. Yeah. If d is negative, automatically it's a yes. Those are my favorite, right? Okay, one more. You guys all right?
Yeah.
We're great. Okay. What's the last one? The max volume. Find the volume of the largest rectangular box. That one?
Yes. Almost the same as 45.
Yeah. Okay. So find the volume of the largest. Can you see past my head or no? Is that better?
Yeah, I can see it. Sure.
Oh no, I mean like the screen.
Oh no, yeah.
Okay. Rectangular box in first octant. Oh, this is like the one we did in the notes. With 3 faces in the coordinate planes and then 1 vertex in the plane x plus 2y plus 3z equals 6. Didn't we do this one in the notes? Okay.
Yeah.
51.
In,
In 14:8. No, it's 53 and 14.
oh, yeah.
No.
No. In 14.8, it's the lower number.
then 14.8.
Okay, and in 14.7 it's 53. Oh, so I'm doing the wrong one.
No, you're doing the correct one.
Okay.
Whether you're going to use Lagrange or
I've done so many. I have them all because like I used to give so much more homework before, so I don't even know. Okay, here we go. I'm doing the right one.
Maybe not.
No.
Sorry, you're making me go back to this. It's correct. It's correct.
Okay.
It's the same problem, just the method's different.
Okay, who cares? As long as, well, I don't know, there's this other cute one right now I'm looking at. Find the dimensions of a rectangular box of maximum volume. Such that the sum of the lengths of the 12 edges is a constant. Oh, okay. Abort mission. Okay. I was like, this one's eerily similar to the lecture anyways. Like, why would I give you such, oh, this one's cute. Okay. Max volume. If you guys just let me, I'll just do the whole section. Extra besides what you need? You don't want that. Max volume. Oh, find dimensions. Of rectangular box max volume such that the sum of the lengths of its 12 edges, how nice they're telling us there's 12 in case you have a rough time with that part, is a constant C. So I don't want to do LWH nonsense, guys. Let's just do XYZ, right? Were you doing LWH over there? You were? Oh, that's sweet. Okay, so we're not. There's 12 edges. There's 4, right, describing each of the dimensions. So we want to maximize what quantity? Volume. So I'll say f of x, y, z is x times y times z, such that my constraint is 4x plus 4y plus 4z is C, some constant. Good? Gradient of F is lambda gradient of G. This is G. Yes?
This is 14.753, right?
Yes.
Are we using Lagrange? Because 14.8 is different.
14.8, I gave you 51.
Yes.
So I'm doing it Lagrange first, and then I'll do it 14.7 method.
This 14.851 is find the volume of a rectangular 3 basic coordinate lengths on the vertex. They're different ones.
14.851 says to do 53 from 14.7. Okay, so gradient of F, what do you have?
Y x, xz, y. Or sorry, yz.
Yeah, you made me nervous. xz, xy equals lambda times
4.
woohoo. Okay. YZ is 4 lambda. XZ is 4 lambda. XY is 4 lambda. That means they're all going to equal each other, right? Okay. 4 constraint equation. Can X or Y or Z be 0? No. X can't be 0, Y can't be 0, Z can't be 0. Then you're not even making a box. Then you have failed at solving the problem. Straight to math jail. Okay, so then we're going to have, let me just set these two equal to each other. YZ equals XZ. So X equals Y. XZ, this is like the same as the other problem. Z equals Y, right? And then where do these go? 4. So then we're going to have 4y plus 4y plus 4y is C. So 12y is C. So y is C over 12, which is also going to be X and Z. So it asks for the dimensions. What would you say the dimensions are? C over 12 by C over 12 by C over 12. Good?
Oh, you have to write it out in the...
Or write it order triple. I don't care. Okay. Good? Okay, other method. So same idea. we have to reduce the number of variables in the function that we're optimizing. So I would just do the same thing. So 14.7 method.
Why are they being multiplied?
No, that's like how you give dimensions, like a 2x4.
Right.
Okay. Or you're going to think of going to in and out, huh? So we have volume is x, y, z, subject to 4x plus 4y plus 4z is c. So I would say let's solve for z. It's going to be 1/4 c minus. Oh no. Are you lost in the sauce? 4x minus 4y. Yeah. Are we okay?
Yeah.
Okay. So then I could say my function of just x and y is x times y times 1/4 c minus, that looks terrible. Hold on. I hate it. I hate it so much. Let me distribute. It looks disgusting. I kind of do want to distribute it through this guy, though. Do you know what I mean?
You should just make a new term like C dash.
Isn't C over
I would do 1/4 c minus x minus y. And then this, watch, this is going to be the cutest one to take the derivative of. 1/4 cxy minus x squared y minus xy squared. Now I feel like, ooh, I'll take the partials and I won't mess that one up. Behold. Nice? Okay. You got to set yourself up to succeed, you know? Like if it looks ugly, most likely you're going to not do a nice job. Okay, here we go. Partial with respect to x.
1/4 cy minus 2xy minus y squared.
Good. We're going to set that to 0 in a second. Partial with respect to y.
4cx minus x squared minus 2xy.
Good. Set that equal to 0. I can divide out y from the first equation because I know y is not going to be 0. So then I have 1/4 c minus 2x minus y is 0. And similarly, 1/4 c minus x minus 2y is 0. So this is a system of equations. Remember, c is a constant. Yeah. So let me write this first nicer. 2x plus y is 1/4 c. X plus 2y is 1/4 c. Let me multiply. Let's switch it up. Let's multiply this one by -2. So I don't have to rewrite both of them. This is what you do when you're especially lazy. Equals -1/2 c. Do you see why I didn't want to multiply the other one? Because I'd have to write, yeah, forget that. Okay, we have things to do. -1/4 c. Wow, we get the same answer. Math works.
If you plug that in,
Then yeah, blah, blah, blah. This comes out the same. And so does z. Whatever. You guys got it? Yeah. Minus x minus y. Yay.
So Lagrange is nice because we also did all the ugly algebra.
Although that other one we did, Lagrange was not better. Yeah, it was so fast the other way. So you know what that says? You can't be a one-trick pony. Okay, that's all for now. Oh, give the video a thumbs up, subscribe, comment down below. What else should we say to them?
Enroll in your class.
Enroll in my class? No, I don't want them to. No.